All right, so this video is going to be about the solutions. Okay, so let's take a look at what solutions are. All right, so some things that you're going to want to keep in mind as we talk about what solutions are, some overarching questions. So when you're making sweet tea, are you supposed to add the sugar when the tea is hot or when the tea is cold? Why? Will salt dissolve in water just by itself, or do you have to shake it or stir it? And which is going to dissolve faster, a sugar cube or loose granulated sugar that you would get out of a packet? So those are some things that we're going to be thinking about as we talk about solutions. So our next unit is about solutions. So we're going to be taking a look and seeing what gives solutions their specific properties. All right, so a solution is a homogeneous mixture of two or more substances in a single phase. They can be in a solid form, gas form, or liquid form. Homo means the same. So homogeneous means the same throughout. This means we're going to have a very even mixture. Here we can see that all of these little white dots are evenly spread amongst the yellow dots. So when we're looking at solutions, we notice it's very even. We don't see clumps, we don't see little chunks here and there, we don't see separation, we see evenness. In a solution, one constituent or part is usually regarded as the solvent. The others are known as solutes. The one that is doing the dissolving is known as the solvent. A lot of the time, your solvent is going to be water. The solute is the one being dissolved, such as salt right here. We're pouring the salt into the water, the salt is being dissolved by the water, so that's our solute. So the solute is the part of the solution that is being dissolved. Usually it's a small amount. The solvent is the part of the solution that is doing the dissolving. It is usually a greater amount. When you put them together, the solute plus the solvent makes a solution. So here's a common example of a solution: hot chocolate. So right now it's springtime. We're not really thinking about warming up with some hot chocolate. But just in case it gets cold and we want to make some hot chocolate, our solute is going to be the cocoa powder or hot chocolate mix. The solvent is your water or milk, depending on how fancy you get with your hot chocolate. I usually just stick with water. And the solution is when you mix them together and you make hot chocolate. Now, when you make hot chocolate, you don't just want to pour the powder in there and drink it straight away. You want to stir it. You want to get it nice and even. You don't want to drink it and have a big chunk of powder coming up your way, okay? So we want to make sure that we have it nice and smooth and even. So we can have different types of solutions. They can be mostly gas or gaseous solutions. We can have liquid solutions like lemonade, and we can have solid solutions, better known as alloys, such as this tooth filling right here. So let's look at some examples of types of solutions. So we can have a gas-gas solution, such as air. This is when I have a gas like oxygen mixed into another gas like nitrogen to make a gas solution like air. The next type is a gas mixed into a liquid. So this would be like putting carbon dioxide gas into liquid syrup to make soda. That's really all soda is just carbonated water with some sugar in it. We can also have a liquid-liquid solution where we have a liquid mixed into another liquid, such as with gasoline. We can have a solid mixed into another liquid. This is a solid liquid solution, such as salt going into water to make seawater. And we can have a solid being mixed into another solid to make a solid-solid solution, such as brass or bronze. Now, with solid-solid solutions, we can't just crush together the two solids and expect it to be nice and even. Instead, we have to do a little trick. We have to melt them down first. So we would have to melt down our two metals, mix them together while they're still melted, and then cool them down to get our solid-solid solution. So these are all very even. We don't find chunks. You wouldn't expect to go get some brass and it be made of a little bit of copper here, a little bit of something else over there. You'd want it to be very smooth and even. Non-examples of solutions, so things that are not solutions, would be like a salad. So every time I take a bite of a salad, I'm expecting it to be a little bit different than the last bite. So in one bite, I might get some lettuce. In another bite, maybe a tomato or a crouton. Maybe I'll get a lot of salad dressing on another bite. Maybe I won't get any on the next one. Okay, so a salad has a lot of different things going on. It's not very even, no matter how well you blend it. Soil is another non-example of a solution. Okay, so I can go out and look at my potted plants outside, and probably every single one of them is going to look a little bit different with the dirt that's in there. So I might find some mulch in one part, maybe a little twig, maybe I'll find an earthworm, maybe I'll find little bits and pieces of rock, maybe some other pieces will be really fine. So soil is very uneven by nature. And then finally, water. Now, water is not a solution because water is just one molecule, H2O, dihydrogen monoxide. It is only one substance. It is not mixed with anything else. Water is water. It's just by itself. Okay, so since it's not by itself mixed with anything else, it's not a solution. It can be made into a solution, but it's not by itself. All right, so solutes in solution are spread very evenly. Okay, so again, we see these little white dots are spread very evenly throughout everything else. They can't be separated by filtration. You can't just pass this solution through a strainer and expect to get the blue powder back up. It's too finely dissolved to do that. However, it can be separated by evaporation. So I can leave this sitting out for a few days, let all the water evaporate, and probably get that blue powder back out. The solutes are not visible when they are mixed well in solution. The solution is going to appear transparent. So here I can still see through this beaker. I can still see that stir rod that's sticking in there. It may give color to the solution, so I can still see there's a blue tint to it, but overall it's still transparent. So since water is such a great solvent, it's very good at dissolving things, it is extremely versatile and useful in a lot of situations. So water is used to carry the following. It can be used to carry silt in agriculture. So in Egypt and other regions where they have big rivers, often the river, in this case the Nile, will flood, bringing a lot of very nutrient-rich silt to the surrounding areas and give a lot of good resources to help crops grow. So in ancient Egypt, they relied on the Nile flooding every year to bring this nutrient-rich silt to help keep their civilization going, keeping all the crops growing. Water is also used to carry salts. So in the healthcare industry, when someone is dehydrated, oftentimes they'll hook them up to an IV bag with some saline solution. If you are deficient in a vitamin, they might hook you up to a different type of solution. Medicines are often dissolved in water to help get them into the bloodstream a little bit faster. In agriculture, again, the nutrients are often dissolved in the water, like fertilizer. So sometimes I have to go outside to my patio and fertilize my plants, and I'll mix in some fertilizer packets to do that. Batteries rely on water to dissolve the ions that are causing the electric flow. And in electricity, water is often used to carry ions to make a good electric circuit. Water by itself is not very electrically active. However, when you start putting ions in there like sodium and chlorine, that's what carries the charge, not the water by itself. In addition, water is also used to carry nutrients and waste around the body via the bloodstream. So most of blood is made up of water. And so that water helps to get a nice, smooth fluid pumping throughout the body that can carry nutrients like vitamins, minerals, oxygen, as well as waste products such as carbon dioxide to get throughout the body. So let's talk about some terms that we use when we're talking about solubility and solutions. So the word soluble means that the substance can be dissolved. Sugar is very soluble in water. Sugar can be dissolved in water. Insoluble means it cannot be dissolved in water. It's the antonym. So oil is insoluble in water. Miscible is specifically when a liquid is soluble in another liquid, such as lemon juice in water or milk in water. Immiscible is the antonym for when a liquid substance is insoluble in another liquid. So immiscible, it would be like oil and water. They don't mix. Notice that miscible and immiscible pertain specifically to liquid solutions, okay? Soluble and insoluble are more generic and can relate to solids, liquids, or gases. All right, so applying the terms miscible and immiscible, let's look at these two test tubes. I see in the first test tube, there's kind of a break in here. We see there's a division between the top and bottom two layers. I can see that because there's a little bubble right here. In the second test tube, it's very smooth and even. So we're gonna say that this test tube is immiscible. Okay, so the two liquids that are in here are immiscible with each other. That means that one liquid is floating on top of the other liquid, and we can see that because of this dividing line. So this might be some oil on the top and some water on the bottom. Miscible, they can mix completely with each other. This might be water and alcohol, okay? So rubbing alcohol and water mix very, very well together. Maybe it's some acid, something like that. Okay, very, very smooth. There's no dividing lines. This is miscible. So water does this because water molecules are packed very densely. What happens is the bonds that form between the water molecules, they're called hydrogen bonds, basically cause them to get very, very densely packed. And therefore they sink down to the bottom. Oil is what we call a nonpolar molecule. Okay, so oils and similar compounds are very even. What we see is that on water, the oxygen likes to hog the electrons for itself. It pulls the electrons away from these little hydrogens right here and concentrates them on this negative end. That means that there's not very many electrons where the hydrogens are. It's kind of like a blank space. With oil, it's such an evenly distributed molecule that those electrons don't crowd anywhere. They're just kind of everywhere. So whenever we have this big separation of electrons concentrated over here, but not here, versus very even, they don't mix. Okay, so that uneven distribution is called polarity, whereas even distribution means it's nonpolar. There's not that division. So a lot of the most valuable properties of water rely on this polarity because of how oxygen hogs all of the electrons for itself and pulls all of them towards this area where the oxygen is. So we say that oxygen has a partial negative charge. The two hydrogens have a partial positive charge each because all these electrons are going towards the oxygen. That's what being polar means. that all the electrons are being concentrated on one area and not the others. So water is known as the universal solvent because more substances dissolve in water than any other chemical. Now that doesn't mean that everything dissolves in water. It just means that it dissolves more than other things. And that has to do with the polarity of each water molecule that we just discussed. So when something dissolves, we see that there are these little pockets that form around the ions. So ions in hydrophilic solutes dissolve really well in water. The Greek root hydro means water. Philic means loving. So water-loving solutes dissolve really well into water. Okay, so again, we have this negative area around the oxygen, positives around the hydrogens. That's just because of how the electrons are hogged towards the oxygen. So let's say that I have a salt, just any generic salt that has an anion and a cation. Let's go with sodium chloride table salt. When I dissolve sodium chloride table salt into water, these two, the chlorine anion and the sodium cation, are going to separate into their respective ions. So we're going to see that the negative chlorine anions are going to be surrounded by the positive hydrogens. We're going to see that the positive sodium cation is surrounded by the negative oxygens. So in other words, if it's negative, it's going to attract the positives. If it's positive, it's going to attract the negatives. So this is the concept of opposites attract. So basically, the ends of the water molecules are going to be attracted to the opposite charge and form these little pockets. So these are called hydration shells. Here's a little bit closer picture of everything. So we can see that we have a salt crystal that's being dissolved, and all of the water molecules are aligning themselves based on the different ions to form these hydration shells around the ions. Here we can see another molecule. So this is like sugar. The sugar doesn't form cations and anions. Instead, it just breaks off into polar molecules. Okay, so here we can see that the little sugar molecules have been distributed very evenly. We still have these hydration pockets going on around each sugar molecule. So since the water is dissolving the sugar, water is the solvent. We can see there's a lot of water here, and sugar is the solute that is being dissolved. All right, so polarity often depends on symmetry. Fats and oils like this, they're hydrocarbons, very symmetrical. There's nothing that's asymmetrical about this. It's very even. That means that there's not going to be any electron concentrations anywhere. It's very smooth. Polar molecules are uneven. We can see that the oxygen here is pulling on the electrons towards it and away from the two hydrogens. These are things like water, glycerol, other types of alcohols, or things with an OL ending. A lot of sugars are examples of polar molecules. Ionic compounds are polar as well. Okay. So again, water molecules are polar because oxygen is more electronegative than hydrogen, which means that it hogs the electrons for itself. That gives oxygen a partial negative charge and gives the hydrogens partial positives. This causes water to form strong intermolecular hydrogen bonds. That is a very important concept, the concept of hydrogen bonds. So water molecules are attracted to one another better than other molecules its size because they have these positives and negatives that draw one another to each other. So what's going to happen is these positive hydrogens are going to attract a negative oxygen. The negative oxygens are going to attract a positive hydrogen, and so forth. So this is what we're going to see. We're going to see that this hydrogen is going to line up with an oxygen. This oxygen is going to line up with some hydrogens until we get a crystalline structure that basically aligns itself a little bit more regularly. So hydrogen bonding occurs because of polarity, and a lot of the important properties of water are going to be because of this hydrogen bonding. So things like adhesion, cohesion, surface tension, its heat capacity, all of that is attributed to hydrogen bonding, as well as why water gets less dense when it is frozen, whereas most other substances get more dense as they're frozen or cool down. So what is or is not soluble in water? Okay, so we use the term like dissolves like. That means that polar solvents can dissolve ionic compounds in polar molecules. Polar dissolves polar. Water is polar, so it can dissolve other polar compounds like salts, sodium chloride, copper 2 sulfate, sodium hydroxide. It can also dissolve other polar compounds like things like sugars, alcohols, anything that's not even. Nonpolar only dissolves nonpolar. So you can dissolve two types of oil with each other, but you can't mix them together. Okay, you cannot put oil, which is nonpolar, very even, with water, which is polar. They don't mix. You can only put like compounds together. So in the next video, we're going to look at why we need energy to be able to change how these occur. So we're going to see how we can take individual solutes, break them apart, and get a solution out of them.